Welcome to this Algebra 2 session on the polynomial remainder theorem. So we're looking at using the polynomial remainder theorem to evaluate and graph polynomial functions. So remainders can be useful. The remainder theorem states if the polynomial f of x is divided by x minus a, then the remainder is f of a. So this seems a little, with just letters, it may seem a little confusing, but as we talk about it, you'll see that it's a pretty easy concept to understand. If you can quickly divide, this provides a nice alternative to evaluating f of a. So if you want to write this down, the first part is something that you want to write down. You can pause in the lower left-hand corner. For an example, use the remainder theorem to find the indicated function value. F of x is equal to x cubed minus 7x squared plus 5x minus 6. And we want to evaluate this for f of 3. So basically what this lesson is about is using synthetic division to evaluate the functions. We've evaluated functions in the past by taking this is an x value and taking it and substituting it into the equation for x. So you can do that as a way to check. If you find substituting the number in for x as being easier for you, I would suggest you do it that way. I'm all about doing things in a way that's easiest for you if you have multiple options. So I'm going to do synthetic division though, and then I'll also show you how to evaluate it for x as we've done in the past. So our divisor is 3. And then we do our little synthetic part of a box here. And the coefficients of our variables and our constant are going to be the row here that we have in the box. So it'll be 1, -7, 5, and -6. And remember, as we talked about with synthetic division, it's very important that you have the correct sign in front of the number. So if there's a negative or a minus in front of that number, you need to make sure that you put it in the table. So again, the first thing we do is bring the first number straight down, multiply the divisor times that number, and place it under the next coefficient. So 3 times 1 gives us 3, and we place that under the -7. Add -7 plus 3 gives us -4. And again, multiply 3 times -4 gives us -12, and we put that under the next coefficient. So 3 times -4 is -12, and we place that under the next coefficient, which gives us -7. Again, multiply 3 times -7 and place that under the -6 coefficient. 3 times -7 gives us -21, and we get a remainder of -27. So that means that f of 3 is equal to -27. Now, if we were to do that by evaluating, as we've done in the past, that means that I'm going to put the 3 in for x. So I will have 3 cubed minus 7 x squared, x is 3, so it'll be 3 squared, plus 5 times x, which is 3, minus 6. So if we evaluate this, 3 cubed is 27. Follow your order of operations. 3 squared is 9, times -7 is a -63. 5 times 3 is 15, minus 6. And follow your order of operations from left to right. 27 minus 63 plus 15 minus 6 will give us -27. Now this whole thing can be put in your calculator. If you want to check your synthetic division here, you can type the whole thing into your calculator and press enter, and you get -27. So what you need to realize here, guys, and this is important, is that this means that we have a point on the graph at 3, -27. So this is a point. This is a graph. We can graph x cubed minus 7x squared plus 5x minus 6. And if we were to graph that, we would see that the graph would go through the point 3, -27 on the coordinate plane. The 3 is the x value. The remainder is the y value. So it is a point on the graph, and that will help you as we work through this lesson and the next lesson. So you can pause lower left-hand corner if you need to. You can also rewind or fast forward. All right, we're going to use the remainder theorem one more time to find f of 2. And I'm not going to evaluate it by putting the 2 in for x. I'm just going to do the synthetic division here. So 2 is our divisor. Divisor comes from right here. Make our box for our synthetic division. Coefficients of x go in the box and the constant on the end. So it'll be 1, -5, 5, 5, and -6. And so I'm going to bring down the 1. 2 times 1 will give me 2, and I place that underneath the next coefficient. Add, and we get -3. 2 times -3 gives me a -6, which I place under the next coefficient. 5 plus -6 gives me a -1. 2 times -1 is a -2, which I place under the next coefficient. 5 plus -2 is a 3. 2 times 3 is 6, which I place underneath the last coefficient, or the last number, which is the constant. And -6 plus 6 gives me 0. So I have a remainder of 0 here. A remainder of 0 means that 2 is an actual factor. Well, I should say is an actual solution to this polynomial. So first let's write out what we have. F of 2 is equal to 0. So that means that 2, 0 is a point on the graph. And 2, 0 is an x-intercept, because whenever the y value is 0, you have an x-intercept. So x equal to 2 is an x-intercept. Or a solution. So you get a remainder of 0. That means that you found an x-intercept. That also means that you have a factor, which we'll talk about in the next lesson. And it also means that you have a solution to the polynomial. So this polynomial on the coordinate plane is going through 2, 0, and 2, 0 is an x-intercept. All right, we're going to move on here. All right, moving on, we have used the polynomial remainder theorem to find at least 4 ordered pairs for each polynomial and then graph. Now, I have to be honest with you. This is a parabola, or a quadratic polynomial, because the highest exponent is a 2. So would I use the synthetic division table that we're going to use now to graph this? Probably not. I would use what we talked about in the last unit for graphing parabolas. Those of you who are new this semester, if you've never graphed a parabola before, then you definitely would want to use this table. But this table is a long way of graphing a parabola. Now when we get to a higher degree, like a cubed, which we're going to do next, you can use the table if you want to find some points. I still am not sure that I would. I think making a XY table is a little bit easier. But you need to see this because you're going to see it on the quiz. So I want to make sure that we cover it. This is called a synthetic division table. You see part of it right now. I have part of it covered up. Let's write down the name, synthetic division table. So the way that you find the rows of this table are by picking values for x that you want to use and doing synthetic division for it, and then listing what you get after the synthetic division in the table. So I'll show you what I mean with the first one here. Your x values go along the side here, and your coefficients for your polynomial go across the top. So we have 1, -5, and 2. So what they did here to get this row is synthetic division using -1 as the divisor. So we're going to do that down here. So -1 is our divisor. We create a little synthetic division here. 1, -5, and 2 are in the table. Bring down the 1. Multiply -1 times 1 is a -1 that goes underneath the -5. And that gives us -6. And then -1 times -6 is a +6. Place that under the 2 and you get an 8. So what we get after synthetic division is what goes in the table across from the -1 in that row. So what we do to create the synthetic division table is pick values of x, and you can see I've picked 0, 1, 2, and 3, and then I perform synthetic division using those divisors, and these are the rows that I get. So doing synthetic division with 0 gives me a row of 1, -5, and 2 at the end. Doing 1 gives me 1, -4, and -2. Doing 2 gives me 1, -3, and -4. And using 3 gives me a final row of 1, -2, and -4. So again, if you look at the example here, this is -1 as the divisor, and I have this row remaining, so I put it in the table. So that is our synthetic division table. Now what do we do with it to get the points? Well, your points come from the first number on your table here and the last number. So that means that I have a point at, let's write that up here. I have a point at -1, 8. I have a point at 0, 2. I have a point at 1, -2. I have a point at 2, -4. And I have a point at 3, -4. So again, these xy pairs are coming from the numbers here and the corresponding numbers in the last row. So -1, 8, 0, 2, 1, -2, 2, -4, and 3, -4. So that gives me points to put on my graph. And again, you can choose any values for x that you want. So let's graph these. -1, 8 would be right here. This is 8 on the graph. 0, 2 would be right here. 1, -2 would be right here. 2, -4 would be right there, and I'm going to mark that as -4. And then 3, -4, you can see that we have a y value being repeated, which should happen because this is a parabola. So remember, we have mirror images of the points. Now, we, with a parabola, always have a vertex, and you can see that we don't have the vertex point here, so it's got to be between these 2 points. So when we connect it, we want to make sure that we go down a little bit below there and back up. So that's our graph. And the reason I know to come back up, guys, is because this is a parabola, and a parabola is a U shape. Okay? The points are mirror images of each other. Now, like I said, I would not do a synthetic division table for graphing a parabola. I would use the tools that we had in the last unit for finding the vertex and graphing it that way. But if you've never done that before, you definitely want to use the table. This can also be graphed on your graphing calculator, as we talked about in the past as well. So you can put that into your graphing calculator just to get an idea of what it looks like if you want to do that too. All right, last we're going to look at a cube graph. If you remember, a cube graph looks like an S, kind of like an S. It has a curve to it. And it can curve. Let me just show you in general here. A cube graph, if I can find some room, will look like this or look like this, depending on whether the coefficient of the cube term is positive or negative. If it's positive, it will curve this way. If it's negative, it will curve this way. So since we have a -2 in front of the a cubed, that means I'm looking for a graph that curves in this fashion. So you can see my synthetic division table here, and I'm not going to go through getting these rows again since I did it on the last one. But this is doing synthetic division with a divisor of -2. I get this row. A divisor of -1, I get this row. Divisor of 0, I get this row. And a divisor of 1, I get this row. So that gives me ordered pairs of -2, 28, -1, 12, 0, 2, and 1, -14. Now I decided that it would be easiest for us to make this coordinate plane by 2's. So this will be 2, 4, 6, 8, 10, 12, and so on. This will be 2, 4, 6, 8, 10, 12, and it'll keep going. So our first point is -2, 28. This will be -2. -2, positive 28 is going to be off our graph. I did not have a graph big enough to do that, so I'm going to put it up here. And then -1, 12. -1 is going to be right about here in the middle. And it's a positive 12, so we're right here. Actually, I think I'm going to make these blue, so don't confuse them with our numbers here. And then 0, 2 is a point, so we have a point right here. And 1, -14. So 1 is right in here, and -14, 2, 4, 6, 8, 10, 12, 14. So right about there. So again, I told you it would be like an S shape, so when you draw it, it's kind of what you want to do here. And it's a little hard for me with this pen, but you get the idea of what it's going to look like. Now, you don't want to try and connect it to be a straight line, because a cubed graph is not a straight line. It is that S curvy shape. So you want to be careful of that. And you can check this on your calculator as well if you want to put it into your calculator to get an idea of what it looks like. And that ends the session on polynomial remainder theorem.